Chapter 4.4 introduces a new rule. It's called the chain rule. So far we have gone over 6 different differentiation rules, and we have been using those intermixing as we do these various problems. What I want you to come across, Chapter 4.4 introduces a new rule. It's called the chain rule. And what this is just another differentiation rule that we can add to the toolbox of the other ones that we have learned. So far we have learned 6 of them, and I will go over those 6 in the next slide. But what we're going to come across is this new pattern, or this new type of function, which we call composition functions. We're going to be looking at that pattern and recognizing that this is a pattern for which I'm going to have to use the chain rule. So when you're looking at these, you don't have to do these, but I would suggest that you do because you can. And what we found is in all of these problems, we're able to use a mixture of these 6 different rules that I've listed off to the side here. So for example, number 6, what you could do is you could use the quotient rule, or what you could also do is rewrite this problem to be x to the negative 1/2 and then distribute that to each one of your terms. And then you can avoid the quotient rule, but then you're just using a mix of these other power, scalar, and constant rules. So what I want you to do is look at this one and how it differs from the ones that we have done in the past. What you could try to do is say, well, I can try to address this what's inside these parentheses first. I can use the sum and difference rule, the scalar and the power rule, the constant rule here. But what's going to happen is, how do you address that exponent of 3? So what I don't want you to do is I don't want you to distribute that exponent to each one of those terms being added in that grouping. Please, please do not do that. Alright, so watch out for patterns like this. This is what we call a composition function. It's a function within a function. So you have this grouping, and then oftentimes you'll have a group brought up to some sort of exponent. And that is the composition function pattern. So just as a reminder of the notation that we've used in the past for composition functions, this was when last year we introduced that hollowed out dot, and how this would be read was f of g of x. So the best way to kind of look at it is this notation right here. Basically and literally, you have a function that goes into another function. Okay, and then same thing here. So how can we split the two functions acting on x? So being that this is a composition function, what I'm going to say is you're going to be looking for an inner function. That's going to be probably that grouping that's been brought up to some sort of exponent. So I'm going to call that inner function, we'll say inner function here, inner function g of x. Okay. So oftentimes we notate the inner function as g of x. Here is what that would be in this situation. However, I'm going to introduce a new notation. We're going to call it u, and this is probably the strongest notation that this section goes by. So either way you want to look at it, it's fine, but you could call it g of x or you could call it u. Alright, so that leaves us with addressing what the outer function is. The outer function is going to be just f of x. We're going to be taking f is going to be the outer function and then an input. So our input is going to be that g of x eventually. But how we're just going to write it is f of x equals x to the third. Whatever we input into our function f, we're going to take that input and cube it. So same thing if we looked at this as f of u. We're going to address that there is some sort of inner function. It's going to be called u, and here we name it. But for now, I just want to say whatever that inner function is, we're going to cube it. So regardless of how you write it, this first way, we would look at it as f of g of x. And you're going to be taking what is g of x, that is the inner function that you addressed, and you are going to put that in to your f function. So again, if I gave you what is f of 2, you would simply say, well, 2 is my input. F of 2, plug in 2, and from that input that you're saying is going to be cubed. So same thing here. Here's my input. That is what I want to have cubed. So here is my input for that x that's going to be cubed. Okay, so I took my g of x and I plugged it into my f of x. Same thing with f of u. If you had f of u, whoops, I wrote it again. What is u? So u would be 3x to the 8th plus 2. That's what you said was your inner, and you're going to take that inner function and you're going to plug it into the f function that you defined, which said your inner function needs to be cubed. And so either way you write it, you're going to get this same answer. So how to derive this type of function or this type of pattern? What we call it is the chain rule, and I pity the fool that doesn't know the chain rule because it's very simple after you study it and get it down. So if you have a function y and it is in a composition function, what you're going to be doing is you're going to derive that function y around your u. So derive y around that inner function, but leave that inner function alone. Okay, so I've written it down here. Then what you're going to do is multiply that by the derivative of the inner function. So derive u around the variable x. If overall your function y is written in terms of x, then you do want to derive in terms of x, but at first you're going to derive it with respect to the inner function, leaving that inner function alone, and then you're going to go back and multiply it by the inner function's derivative. You can see that same notation down here. If you want to write it like f of g of x, well then you're going to derive the f function around the g of x, leave the g of x alone, but then derive the inner function, that g of x. So I'm going to do this in a very fluid motion, and then I'm going to show you what it would look like if you break it apart by that definition of the chain rule. So again, what the whole chain rule is about is deriving the outer function with respect to the inner. So I'm going to just use, I can see, here's my inner function, it's brought up to the third. So how you can look at this is just a power rule. It's just something brought up to an exponent. So I'm going to bring down my exponent, leave that inner function alone, but then reduce my exponent by 1. So I'm going to get to the 2. But then you have to multiply it by the derivative of the inner function. So this will just be piece by piece, power rule and scalar. So I'm going to just bring down that 8, multiply it to that 3. You're going to get 24x to the, and then reduce that exponent by 7. And then plus, you could derive this constant, but hopefully we're recognizing constants just drop out of the equation. They just drop out. So here I'm just going to close it. So in the end, what you're going to be getting is, if you simplify this, I can take this 24x to the 7th times 3, you're going to get 72x to the 7th, and then times, here's a grouping, 3x to the 8th plus 2 squared, and you can just leave that. So that is the most fluid motion that I could do for the chain rule. You'll eventually get there, but now let's actually break this up. So I'm going to address u, or find my inner function. It's and name it u equals 3x to the 8th plus 2. Right? And then I'm going to say, well then my overall function, f of u, is equal to, and then it would just be u cubed. Okay, so if you wanted to, we could write this as y equals u cubed, same thing. So I'm going to use that rule, dy dx is equal to dy with respect to u first. So I'm going to go over here, and I'm going to find what is dy with respect to u. So I'm going to derive around that u. This is just going to be that good old power rule. So because u is what I'm deriving with respect to, oops, sorry, this is du. I'm deriving with respect to u. So I'm deriving my function that I've named u cubed, and I'm doing it around u. So here it's going to be 3u to the 2nd. Alright? So then I'm going to go over here and say, because not only do I need dy du, I've gotten what dy du is equal to. That's this right here. What I also want to recognize is I need to go back and derive that inner function. So if u is equal to 3x to the 8th plus 2, then du with respect to x is going to be dx 3x to the 8th plus dx of 2. And then you're going to drop that down. You could bring that 3 out in front if you want, but I know I'm going to multiply it on eventually, so I'm going to just write this as 24x to the 7th, because I dropped down my exponent, plus 0. So this right here is my du dx. So all in all, I can write this down. dy du was 3u squared. times my du dx, or the derivative of that inner function with respect to x, was 24 x to the 7th. I can combine these right here to be 72 x to the 7th. And then here's the thing, here's u squared, but we wanted to overall derive this function, or this y, in terms of x. So what you can do is then sub back in what u was in terms of x. So it was 72 x to the 7th, oops, times 3x 8th plus 2 squared. So there are your practice problems. I also want to show you a video at this point.
I see you deriving in class during calculus, and you got f of u, which you want to find the derivative of. It's just f prime u and a du2. It's just the chain rule, a great calculus tool. Do you use it when? You use it when there's an inside and an outside that you can write as f of u. Another calc tool is the product rule, and I know you can get it done. The slope of the product of functions 1 and 2 is 1d2 plus 2d1. I pity the fool who forgets the product rule. Oh, that's how I ends up. It's just 1 and 2 plus 2d1. There's just one more rule. Wait, what's the chain rule again? I see you deriving in class during calculus. You've got f of u, which you want to find the derivative of. It's just f prime u and a du2. Said it's just a chain rule, a great calculus tool. You use it when? You use it when there's an inside and an outside that you can write as f of u. For quotient, 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 you don't have to pull out your head. Your head, your head, your head. Cause it's just low d high minus side kilo all over the square. The square, the square, the square. To find dy, dx, dy, dx, dy, dx, baby. But what about that tangent rule? Oh, I see you deriving in class during calculus. You got f of u, which you want to find the derivative of. It's just f prime u and a du2. It's just a chain rule, a great calculus tool. You use it when? You use it when there's an inside and an outside that you can write as f of u.
Number 1, all it asks you to do is they give you this function and they ask you to identify the inner function and the outer function. So they kind of have this chart that you need to fill out. So you would just say, well, u equals g of x. What is that? What is our inner function? In other words, it's gx, or 6x minus 5. Then it asks you what is y, the overall function, or in other words, f of u. So when you're looking at this, again, no matter what type of notation you prefer, you know that it's u to the 4th. Okay, so there you have it. For number 9, all we're going to be doing is finding the derivative. So I'm first going to do the fluid motion, and then I'm going to break it apart. So the most fluid motion would look like this. If you wanted to find the derivative of g of x with respect to x, you're going to first derive around this inner function. So recognize this was your inner function. You basically have 3 times u to the 4th, and we're going to just bring down that power, multiply it to that scalar. So we're going to get 12 times 4 minus 9x. And then bring down that exponent by 1, and then multiply it by the derivative of this inner function. So it's a constant, so it's going to be 0 minus, and then we have this 9x. In the end, when you derive that carefully, you're going to get negative 9. So when you simplify this all, I mean basically you just have negative 9 times 12 is going to be negative 108, and then 4 minus 9x cubed. So to break this apart, actually, let's recognize this as my inner function again. So here u equals 4 minus 9x, and then y, therefore, would just be taking that u and bringing it to the fourth. Oh, and pardon me, there's a 3. Okay, so we have 3 times that inner function to the fourth, and what I'm going to use is that chain rule. So I ultimately want to derive with respect to x, but first I'm going to just derive my outer function with respect to u, and then I'll go back and multiply it by the inner function's derivative. So at first, let's look at what is dy with respect to u. So equals, and then here du of 3 times u to the fourth. So here, if you were just looking at the derivative of this with respect to u, being that u is our variable, I'm going to pull that 3 out to the front. We have 3 times the derivative of u to the fourth, so that was the scalar rule. And now I'm going to tackle just the power rule, so it's going to be 3 times. I'm going to take that 4 down as a multiplier and then reduce my exponent by 1. So this is going to be 12u to the third. Alright, then not only do I need my dy du, I've got that, so this is going to be dy, or the derivative of my function with respect to x is this, 12u to the third, times, I'm also going to need this du dx. So I'm going to go back to my inner function and figure out, well, what is the derivative of du with respect to x? That's a u. That is a u. Equals, so we're going to say d, the derivative of this with respect to x, is going to be the sum and difference rule. I'm going to just derive what is 4 minus the derivative of 9x. And then here is a scalar, so I'm going to pull that out. d dx of 4 minus 9 times d dx of x. And that's to the first power technically. So here it's the constant rule, 0 minus 9 times, because that was a scalar. And then this is going to bring down that 1 x to the 0, that's just 1. So in the end this is equal to negative 9. So you can see I'm going to be getting the same results here. This is negative 108 u to the third, but because we wanted to derive with respect to x, don't forget to sub back in what that u is equal to. It was over here from the very start, 4 minus 9x, and then to the third.